Lecture 3, Fluid Statics. Okay, the learning objective of the lecture 3 to 6. The first, determine the pressure at various locations in the fluid at rest. The second, explain the concept of the manometer and apply the appropriate equation to determine the pressure. Third, calculate the hydrostatic pressure force on the plane curve surface, submerged surface. And the last one, calculate the buoyancy force and discuss stability of the floating or the submerged object. Okay. Our case is static fluid is in equilibrium. There is no velocity gradient and no viscous stress or no viscosity. Hydrostatic force comes from the pressure and its weight of the fluid. This term represents the different condition of the fluid, steady and unsteady. Steady means constant with time, unsteady and constant with time. In viscous and viscous, it means including viscosity. In viscous, it's not including viscosity, but viscous is including viscosity. And in our case, is we focus on incompressible fluids for water, mainly water. Next topic is pressure and the pressure gradient. This figure shows the weight. Okay, this is the weight of the fluid in the static. This one, and the dimension with the width del y, and the height del z, and the depth. This is inclined length del s. Okay, and there are pressure from py, pz, and ps. Py, pz, and ps. Okay, and assume that is weight is very small. Pressure at all surface are equal. For the weight of this weight of the fluid is equal to the volume times rho g. Okay, so we can prove that the volume is cubic meter times density kilogram per cubic meter and time mass per second square. So in this case we can get the Newton, okay, for this unit. So this so this for the weight of the weight of the fluid. Okay, if we write equation for equilibrium equation for summation of force and horizontal force on y direction, so we can write this first equation, and for the vertical equilibrium force is equal to the second equation. If this is a right triangle, so it means del s sine theta equal to del z, and del s cos theta equal to del y. We substitute in the first equation, and we can prove that the ps equal to pz. This means pressure, it doesn't change in the horizontal change in horizontal. And another do the same way for substitute in the equation 2, and you can prove that the pressure increase in vertical depending on rho and del z. Okay, and in case of very small weight, del z is equal to 0. So finally you can prove that pz py equal to ps pz and p. This means the pressure at a point in the fluid at rest or in no motion is independent of the direction. That is summation of this.